I would like to show you two line graphs that you really need to be familiar with, because you could get exam questions where you need to do a little bit of analysis or plot the graphs. And I'm not talking about the graphs of like rate of reactions, like the order of reactions, which have very specific shapes, and you need to know them by knowing the meaning of each graph. It's different. So the basic graph is y is equal to mx plus c, because this is a line graph where, well, we have y-axis, x-axis, m is the gradient, and c is, let me write it down, is the intercept with the y-axis, while m is the gradient. There are two equations in two different topics in A-level chemistry that may be interpreted with this type of graph. One is the Gibbs free energy equation, delta G is equal to delta H minus V delta S. So a common exam question that I've seen before is considering delta G being our y-axis and the temperature being our x-axis, okay? So the graph will look something like this. We have delta G here and T over here. And well, depending on the type of the values that we have for this reaction, it could look something like this. There are some points that are important to consider, but the important thing is that I want you to recognize, to be able to recognize if an equation, simple or not, can be rearranged or can be structured as a line graph, because the line graph is really useful to identify the values, because if we analyze this one, considering T is X, whatever is next to the X-axis would be the gradient. So from this graph, the gradient, so changing y over changing x, would be our delta minus delta S, so the entropy of this reaction. While the C, so the intercept with the y-axis, would be this one, and that would be our delta H. Okay, so we can see then, well, the units, I don't want to go into more detail, just notice the structure of the equation and the structure of the line graph. Okay, because not only you may be asked to identify values from the graph or maybe even plot a graph, but also also interpret a bit what the values mean. Okay, so in this case, we're talking about Gibbs free energy. So if we cross this point above delta G is positive, so if a delta G is positive, the reaction is non-spontaneous. Below this temperature, delta G is a negative, so we know that below this temperature, the reaction is spontaneous. Then we can also analyze the delta H and delta S. Delta H, we can see that it's a negative because it's below zero, so we know that it's an exothermic reaction. And then we can also find that the delta S. So the delta S, do you want, maybe try one moment to think about, okay, what would it tell us about the reaction, this specific delta S, if this is the shape of the graph? So I know it's a bit tricky question, so if you couldn't get the answer, if you didn't understand it, that's okay. I want you to think about the gradient. Gradient, so our M is changing y over changing x, okay? So changing y over changing x. We can see that the line goes in this direction, so we know that it's going to be a positive gradient, okay, as value, because it's like a line that goes up. A negative gradient would be a straight line going down, okay? So this would be our negative gradient. In this case, though, we have a negative. So because we know that the meaning of this M is minus delta S. So if this is a positive gradient, this tells us that it's a negative entropy value. And this tells us that in this reaction, the entropy is decreasing. Okay, so what it means is that either the reaction is more ordered, or that there is a decrease in number of particles. In more order, I mean, it could be changing physical state, like from gaseous to solid, okay? But in fact, if you think about the meaning of delta G in general, this graph makes sense because we know that when we have a reaction that is, I might need to clear up a little bit the colors here. A reaction that is delta H being exothermic, and delta S being negative, so decrease in entropy, we know that the feasibility of this delta G depends on the temperature. In fact, we can see here that above a certain temperature, delta G would be positive, because we know that this term in general would be also positive, so would be bigger than the delta G. But it all depends on the value of the temperature. So I hope you can see this one. Otherwise, I have another video about the signs of the entropy, which could be really useful to watch. Okay. Point to take away, to go back to what I was saying at the beginning, the importance of the line equation, because this is one type of equation, so the Gibbs free energy equation, that can be interpreted with a line graph. But it's not the only one in A level, so now I would like to talk about the second one as well. The second equation that mathematically is just a line graph, yeah, but it's Arrhenius equation. So Arrhenius equation, yeah, it's the equation used to calculate in the rate of reaction topics. Is the equation that helps us calculating the activation energy. And there are different forms of the equation. And I'm going to write down the equation that, like the not linear equation. So K, so the rate constant, is equal to A, which is the is a frequency factor, it's called, but it's just a constant, times by the exponential of minus activation energy over RT, R being the gas constant and T being the temperature in Kelvin. So this equation, Arrhenius equation, want to know in the rate topic. Exponential, we don't like that so much, yeah, which means that we can remove the exponential by taking the natural logarithm of the whole equation. And this will take a different form. And let's see if you can recognize why mathematically that's relevant. In K is equal in A minus EA over RT. Okay. So this, considering that in K, we know most of the time because we can do it experimentally. So we can find the initial rate of experiments, and we can just find quite easily the rate constant of a reaction. And considering that temperature is something that we can control experimentally, can you stop me and think for a moment how this equation could take the linear equation and maybe also plot an hypothetical graph for this? So I know it's not an easy interpretation to do, but useful, because once again, we are able to calculate things by just using this equation and this simple graph. So of course, y-axis is normally your dependent value, so what you measure, okay? Your x-axis is what you control, so your dependent value, but in general, y and x-axis are values that you can actually get either from an experiment or that you're provided, okay? So the graph will look something like this, and then we will relate to that. So the values, they're quite tricky, because doing the so the natural logarithm, so ln, no, in the natural logarithm gives us negative values, so it will have this shape. But on the y-axis, we will have this ln k. On the x-axis, 1 over temperature, because we know that the temperature is in the division sign right here. So the calculation that we do, we get the temperature, and then we would plot 1 over T. So this equation will take this form. Wait, I need to move my camera 1 second. Okay. So this equation will take this form. A natural logarithm of K minus EA over R times by 1 over T. This, as I wrote it here, is exactly the same as this one. Yeah, because temperature, I've just separated the temperature, but is exactly the same. And then we have a plus ln A. So we arrange the things a little bit, and this makes this equation a lot more similar to the linear equation, because our y-axis will be the natural logarithm of k. Our m is minus EA over r. X is 1 over t because m is always times by x, so whatever is next to the x-axis. And then this is our plus c. Okay, which means that this is useful, and normally it would look something like this, a straight line. The gradient of this, which is always change in y over change in x, is our m, is going to be equal to minus EA over r. While our intercept with x-axis, so somewhere there, it doesn't matter so much now, it's the plus ln, so sorry, the natural logarithm of a, I always call it ln, but the natural logarithm of a. And as you can see, y x-axis. So normally this, you're required to do this either from the values, either like you might be given the values for K and temperature, and you have to plot the graph. So this could be a big open question, or you have already the values and you just need to find the gradient. Because finding the gradient, let's call it M, so that's our gradient, it gives you the whole minus EA over R. But we want to find the activation energy normally in this type of questions. So we will need to time the gradient by R, and we know that that will be our value of minus EA. Okay, so it would be just A because, well, it's just a negative gradient normally. So it would be the activation energy. Important to remember, activation energy, it's a positive value in kilojoules per mole, because it's a positive value. So we need to remember to that we have the minus in front, because the activation energy from theory, so is the minimum amount of energy required to start a reaction, will have a positive value, kilojoules per mole. Okay, so here, little revision for Gibbs free energy and activation energy. But the point of this was how we used simple linear graphs, linear equations to find some unknown values in an equation. And those are the two that are more likely to come up in an exam paper. So I hope this is helpful. So this could be one type of question where we apply this linear equation and the Gibbs free energy. For marker, if you want to try, you can stop it and give it a go to the question, and then I could correct it. And this is for the Gibbs free energy. I haven't seen an equation where you have to plot it, but interpretation mostly. While for the Arrhenius equation, very common is this type of question where either you're given the equation or you're just given the values. But notice that you know that you're talking about Arrhenius equation, so something in your mind should always click like, oh, linear equation, linear graph. And if we have the exponential form, we know that we need to use the natural logarithm form instead. Okay, but it's the typical graph that you may be asked to do. And normally the other type of question would be using the graph, calculate the value of activation energy in kilojoules per mole. So this is another very common question. Could take different forms, but this is what I mean by using the linear equation with the graph, and then the gradient would you normally need to calculate the gradient to find a specific value. So that's another exercise worth to try.